Hey. Shoot, you want to get up on the couch? Hold on, I'll help you. Yep. Oh, gotcha. You get a walk later. Just rest. Oh, that's good. All right, let's get started. I am more than happy to take questions today. So our topic is maps. We've looked at this a little bit well, I haven't looked at it all, but you've seen these a little bit on the MP in a couple of places, which we can look at if you're curious. And this is something that you'll have to do a little bit of work with on for the next part of the MP. A map is a tremendously useful data structure, and hopefully the next couple of homework problems will give you a little sense of exactly how useful it is and the type of problems that are good fits for a map. But a map is really useful. There's a question about, how do maps differ from dictionaries in Python? They don't. They're the Java equivalent. There's a portion, let's see here. There's a bit of this where we kind of talk about a couple of other maps are really, really common data structure. And I could have chosen more examples here. Go has maps. I suspect Rust has maps. C++ has something that's probably sort of like a map. They use different terms for them. Dictionary is kind of the Python. I don't know if dictionary is a Python term, but it's used in Python, right? So a Python dictionary, I create. And again, my Python is pretty rusty, but I think this works. I create one using these curly braces. And then I can use bracket notation. And that's kind of the difference between some of these other languages and Java is that in Java, map is an interface, and a map implementation implements the interface. That interface includes methods like put and get. So you can think of this as essentially doing a put, right? So this is putting the value me, or it's establishing a mapping, right? It's putting a mapping in from the key test to the value me. That's establishing a mapping. In Java, you would do this by saying, I equals new map, and then you would say I.put, and then you provide the key and the value. JavaScript has something that's like a map. In JavaScript, these are sometimes what these are in JavaScript is they're actually anonymous objects. They can include nested objects, they can include functions and things like that, but you can also just use it very much like a map in another language. And then Kotlin, which is sort of a Java successor, it's a language that interoperates with Java but provides different syntax. It also has maps. I think it uses internally some of the built-in maps that are in the Java standard library. But the syntax is nicer. It gives you this bracket syntax that you may be used to in other languages. And you can actually play with this in our playgrounds actually support Kotlin as well as Java. So this is the equivalent. In Kotlin, I'm creating a mutable map, which allows me to modify the keys. I have to tell it, like I do in Java, what the type parameters are for both the key and the value. So this is a map that maps from strings to strings. And then once I've done that, now I can use the map very much more like I would use a dictionary or an anonymous object, a dictionary in Python or an anonymous object in JavaScript by using this bracket syntax rather than using put and get. Internally, you can imagine that these are converted into calls into put and get where appropriate. I think you can also actually do, let's try this. I can do put, let's see if that works. Yeah, that works as well. So I can still use this syntax in Kotlin, but I have access to, a little bit of of a nicer syntax that uses this bracket notation. All right, so, and then, this is maps, right? I mean, this is what they are. One way maybe that might help you to think about maps. I mean, on some level, I think the best way conceptually to think about a map is that it stores mappings. Mappings map a key to a value. So when I put a key value pair into the map, I'm establishing that mapping. The map stores that mapping. And then I can ask it for values based on a key, right? So it's almost like a lookup table, right? It's almost like you had a little piece of paper and you wrote down, okay, when someone comes in and asks for me, I should return 5 or whatever the value is. And I can maintain, the map maintains those mappings internally. Today's homework problem is one example of how to use a map. We'll have a couple more coming up that will give you more practice with this. But, in terms of just general purpose computing, the types of problems you solve in the real world, I think that, a linear data structure, something like a list, arrays are a little bit too limited. It's nice to be able to add and remove things. So lists are kind of a nicer thing to use. Understanding how to use lists, understanding how to use maps or dictionaries, it's kind of all you need. I'm not going to say it's 100% all you need, because there's some places where, you might need a more specialized data structure, particularly if performance starts to become a concern. But overall, you can solve a lot of problems in the world with those two data structures, a lot. And so understanding how to use both of them is pretty important. In the past, we've covered maps a little bit later in the class. I wanted to do them earlier this semester, partly because they're super useful, but also partly because you're going to need to do a little bit of work with them on the MP coming up. So I wanted you to see them before that. And again, we'll give you next couple of homework problems. We'll give you some practice on working with these. All right, any questions about maps, how they work, what I might do with them? I'm happy to go through some examples of different applications where I might use a map. Any place where I have a key that I'm going to frequently look up stuff by. And a lot of times, when we go through one of the examples in this, we look at how to store information about people in the map. But on some level, if you think about it, humans have created some of the data that we've layered on top of the world really exists in a way that fits very nicely into maps, right? So maps work really well whenever I have a key that I'm going to use to look up information about something. And if I know kind of a priori or ahead of time what that key is going to be. And so if you think about it, many times, something's wrong with the cat. Many times in the real world, we create those keys so that we can use a map-like data structure. So, I know that you guys are told by people here at the university, and this always makes me a little bit sad, right? But it's like every time you email anyone, include your university ID number in the email, right? It's like we've turned you into numbers, right? But why do we do that? Or sometimes if you email me or other faculty, particularly using a non-Illinois address, I'll write back and say, please email me from your Illinois address. The reason is that Illinois email address contains your net ID. Your net ID is actually really important to me because that's how I look up information in our, various databases and stuff like that about you. So if you email me and you say, I'm having some trouble with the quiz, or, my MP doesn't seem to be submitted properly, one of the things that I do in order to access information about you in our tools is I need that piece of information. I need that key. Whether it's only, I use net IDs for stuff. There are other people at the university that do use ID numbers. I think ID numbers are very dehumanizing. It's not like a net ID is super humanizing, but at least it sort of resembles you. And I can also use it as an email address, obviously. That's the other thing that's really useful about it, is that when you email me, I automatically get that piece of information. So a lot of times I'll grab that and then I'll use that either to look up information in our database or to use it in one of our systems. And the reason is that that's a key. That's a real world key that we've set up that allows information in the university to be stored in a much more efficient way, right? And it also makes up for the fact that a lot of the other pieces of identifying information about you are not very unique. Your name is not unique. Some of you it is. When I was growing up, my name was Jeffrey Warner Allen. I had a hyphenated last name. And yeah, it was pretty unique. I was usually the only Jeffrey Werner Allen at any. I was usually the only Jeffrey with the G. I grew up in the Midwest, and I don't know, G Jeffreys really haven't caught on. But the point is that your name is not unique for many people. And so, and even attempts to make your name more unique, it's like if I include your middle name and whatever, it doesn't help. So that's not unique. You know, if I had your birthday, still not unique. A lot of states, I mean, how many John Smiths are there in the country that were born on a particular day? Probably several. So, you know, organizations that need to track information about people frequently have to create some type of key so that they can look up something in something like a map or a database, right? So, you know, in the United States, people, I don't know who gets one of these. I think many people do. You know, you get a social security number. And so, you know, that social security number identifies you uniquely, and that's how you gain access to certain things. Now, there's problems with that system, actually. A lot of people have pointed out, for example, if I guess, so one of the things that you want with an ID is you want it to be unique, but you also want it, you don't want it to be, in certain cases, you don't want that ID to be super easy to guess. Or let's put it this way, if I make up an ID randomly, I don't want it to actually be likely that it's a valid ID. And it turns out with social security numbers, it's pretty easy to generate a social security number that is a real valid social security number. I don't necessarily know whose social security number it is, but even in, you know, there's ways to just kind of generate one. There's some structure to them that I don't completely understand. But anyway, they don't have enough digits either, right? So it's pretty easy to generate one and to assume that that will actually map to maybe a living person, maybe a dead person, and that causes some problems. Anyway, all to say that, you know, this idea of looking up things, looking up a value, that value can be a lot of different things, right? But a lot of places, you know, this is why, you know, a lot of times when you fill out forms, you're required to put down this particular piece of information, your social security number. That gets used, that number, at least in the United States, and again, I don't think this was intentional, but that number is now used as a key by a lot of different systems, right? Because it's assumed that everybody in the United States, or all people that have a certain degree of citizenship or something, will have a social security number, and they're unique. So your bank uses it now as a key to look up your account, right? You know, if you go buy a car, they might use it or whatever. I mean, it gets used all over the place because your name's not unique, you know, and so this is a unique identifier that we've created for people. If I recall correctly, I don't know, some of you that are from India can probably explain to me how this is going, but at some point recently, the Indian government decided they were going to try to institute a similar program where they were basically going to try to enumerate all the people that were living in their country, which is tough because it's huge and, you know, parts of it are quite rural, and so they were coming up with some sort of similar national ID system, and you can imagine that there's a lot of really good reasons for doing this. Let's see here. Are there maps that can map? Okay, some good questions. How do we implement some algorithms with maps? So you have a chance today. First homework problem. We'll do a few more homework problems where we'll show you a couple common uses for maps. But you can use them. I mean, it's just another tool in your belt. You know, and, you know, going forward, I think particularly in places where we think maps might be a reasonable solution, we'll probably just allow you to use them on the homework problem if you feel like they're helpful. I'll just probably make sure that everything in java.util is available on certain homework problems. Now, you know, if we have a quiz question where we're asking you to implement part of a list, I'm not going to make java.util that list available. But anyway, yeah, I mean, so today, tomorrow, and Friday, we'll do map homework problems, and we'll try to give you a couple of examples of places where they can be used. Hash map is one of the map implementations that Java provides. We use it in a bunch of our examples today. It's not the only one. So you think about, you know, map is to hash map as list is to array list. It's one implementation of this mapping concept, right? Map in Java is an interface just like a list. There's no implementation that goes along with the map by default. You have to provide one. Mapping is an idea, right? It's a concept, it's an abstraction. So hash map we use today. You can also use tree maps. You could implement your own map using a different strategy. Let's see here. Are there maps that can map to variables that can be updated, like declare variable, map test variable, print mapping, update variable, print mapping? It does not have new variable value. Wait, are you saying are there maps that can map to variables that cannot be updated? printing mapping does not have. So maps store references. So actually, that's a good question. Let's look at this together. All right, so we'll jump up here. So maps store references. Now, if you use strings, keep in mind strings are immutable, and so there's no way to update a reference. There's no way to update the value of a string after it's created because strings don't do that. Oh, hi. What? You're in the way again. Yeah, you don't want to play with these. Sorry, I've got some cords on the desk, and they've attracted interest from the cat. Okay, so let's look at how maps work. Let's create a different type of object here. So we'll say public class cat, and then we'll have that class have an age variable, and we'll allow that to be set because it's. You know what? Can I use a record here? Please, Java, let me do this. Double age, not work. Oh, why does it not work? Sorry, I'm so over implementing all these setters and getters for things. Oh, records are okay. Never mind. Records, you can't change the value, but of a record field, not good. Okay, so we'll have to do this with the class. Cat's here. We'll do it with. So let's imagine we have a cat class, and I allow you to set the age. I hate Java. So much ceremony. Okay. Double get age. Return age. And then we also need a setter. All right, goody. So now let's make this a map from strings to cats, which we can do. Cats are Java objects. I can put them in a map. Hi, I'm going to put you in a map. Which doesn't know what that means. All right, so we'll say map.put. No, don't knock that off the desk, please. New cat. And how old are you? You're about 6, I think. So that's good. I'll say system.out.println map.get is. So that'll give me a cat, and then I'll call it get age. All right. So now let's do map.get is .set age 7. Just had a birthday, and then we'll print off this again. Yeah. So what's stored in the map is a reference to a cat. If that object has fields on it that can be updated, like I just did, then I can do that without changing. You'll notice I only did one put into the map, that cat object. And then if I have setters on that object that I can then utilize, I can utilize them fine. With strings, again, strings are immutable. So once I create a string, there's no way to change the value of that string. All those string operations, remember things like trim, they return new string objects. They actually don't modify the string that they're called on. But it's also possible that I've misunderstood this question. Sorry, with primitive types, you want the variable to update. I'm confused. Okay, it should if you put a new value in for the map, it will update, right? Let's try that now. I feel like I'm not understanding this question, so you're gonna have to keep helping me here. So let's create a new map. We'll do this from strings to integers. We have to use the box type. So anything that goes into a map needs to be an object. This is another limitation of maps, and so we have to use these boxing types in Java. Happily, Java will sort of do the boxing and unboxing for us. We'll do another map, and we'll say, and then we'll do another map dot put, to some value, and if I print that value, right? And now let's update it. Oh, hold on a sec. Oh, I'm putting it into the wrong map. Or I'm doing my printlns out of the wrong map. Yeah. So you can always update a map Again, I suspect I'm misunderstanding this question somehow. Yeah. So one of and actually let's look at that together, right? So if we go, yeah, this is in the lesson, but we can do it together. So a map is an interface, right? There's no implementation for it. This is a slippery concept. I can see some of you struggling with it, and that's fine, right? I think this is a really important conceptual idea that can take a little time to wrap your mind around. So remember, an interface is like a contract, right? The contract sets up expectations for the class that implements the interface, but the contract does not implement the interface. The contract just says, here's what something needs to be able to do if you want it to be able to act like a map, right? And this has quite a few methods in it. You'll see a fair number of them are default, right? Meaning that you don't have to implement them. But if you really wanted to create something that implemented a map, you would go through here and you'd have to, and some of these are optional, right? Clear, contains key, contains value, right? What else do we need? There's some static things as well. I don't know exactly if you have to implement those or not. Equals, right? I mean, that we have to do. But the real heavy hitters here are get, put all is optional. Put if absent looks like something that we need to do. And then replace, right? So it's really the core operations that involve updating mappings. You could, like we did at the bottom of the lesson, you can implement your own map. We didn't finish the job because it would have taken another half an hour probably, maybe even longer to go through and actually get all of the different operations checked off. But if you had some way of creating your own map and you felt like it was going to be more efficient than Java's built-in maps, and you might be right for certain applications, you could create something that implements a map interface and then you could pass it to anything that expected a map and it would work the same way. The map interface sets up this expectation, and as a user of a map, you can expect that anything that implements a map behaves the same way, right? Now, there could be bugs, right? So I could implement this and have it do nothing, and then that would be very useful, and the people that tried to use it would be unhappy, right? So the idea is that you have to implement this properly and needs to adhere to certain expectations about how the map works. Sorry, let me check on what are you doing? Oh, I see. That's what you want. So that's the map sets up the contract. Hash map is one implementation that's included in the standard library. But if you look, there was a couple of others, right? There's something called some of these are not super interesting. There's something called a linked hash map. This is a hash map with predictable iteration order. And so one if you think about a list, right? When I iterate through a list, what do I expect to happen? I expect to see a certain number of values in the same order. When I iterate through a map, it's not exactly clear what should happen. I want to see all of the mappings that are stored. So iteration should give me all the key value pairs that are stored in the map. But what order should they come out? And that's less clear. With a list is an ordered data structure. A map stores these mappings. And so, so I think the idea here is that a hash map does not. You'll see that it implements. Does it implement? It does not implement iterable. Let's see here. Does this one implement iterable? I think it has an iterator that you can get out of it. Oh wait, hold on. Is that part of the map? Actual map interface? Let's look. Boolean map. Let's see if there's an iterator. Okay. Okay. Values, right? Yeah. Anyway, so the point being that there are multiple implementations of maps. The one that looked interesting to me was this tree map. So let's check this one out. Yeah. So this is a map. We could use this just like a normal map, except it stores the mappings in something called a red-black tree, which is a particular type of tree data structure. Let's see here. Yeah, that's pretty cool, right? So you can look at certain operations. So for example, contains key for we looked at get and put when we implemented our own map, right? Let's see if there's any information about that in the actual hash map thing. Let's see. It says this implementation provides constant time performance for basic operations, get and put. Okay, so that's cool, right? I mean, constant time is good. And it does this essentially, if you go through today's lesson and you look at how we implemented a map, it does this by making sure that the array that is the front of the hash table is an appropriate size. However, if you need to do contains key, that I think is going to be slower. So let's look here. Yeah, contains key, I think, for certain map implementations might actually have to go through the entire. It shouldn't have to go through the entire map. Yeah, I don't know. It's a good question. I don't know why you would. I don't know what the advantage of a. I mean, I'm sure there's an advantage to a tree map. I'm just not exactly sure what the advantage is, but we spent a little bit more time looking at it. We could figure it out. All right. Go back and see if we have other questions. Oh, okay. Hold on. Let's see here. Oh, yeah. Not with. No. Yeah. So I'm going back to Ben's question about maps, and so let me actually just drag that into the playground where we can mess with it. And we'll talk about why. That's a good question. Okay. All right, so here's the question. If I look at this, you'll see that after I update my test variable, the map hasn't updated. And that's actually really, really important to understand. So what happens when I put something into a map is that this is a primitive type too, so it's a little bit more confusing. So what actually happens is when I insert this to a map, Java's going to box that int in an integer. And when this is something that only happens when I actually put something into the map. And so what's actually stored in the map is a reference to an integer that contains the value 1, 2, 3. I'm pretty sure integers are also immutable though, so that's actually no way to change their value after they've been created. When I update this later, this local, so the map doesn't actually know anything about this local variable, right? The map has this reference to this integer in it. Changing the local variable is not going to help. Even if I use a string, right, it's also going to behave the same way. So let's create string to string, right? Same thing. And that's because what's actually happening here is that I'm copying the reference into the map, right? So it's kind of like I have a small whiteboard coming tomorrow that I'll start using, but remember what we did. Well, I'll try to draw this out. You're in the way again. I know you like that. Oh, where's my marker though? I'm trying to help, huh? All right, so here's, let's see here. Let me draw it after that first. All right, so I've got test, and that refers to this string with the variable with the value test. All right, so here's what it looks like after I finish with that local variable assignment on line 5. Once I put that into the map, what it looks like is I've got, what's my map called? It's called map, right? At this point, I've got map example. And that also now has a reference to the same string, right? So local variable test has a reference to the string literal test. Now I've copied that reference into the map. So later, when I change that local variable, right? So now I'm going to change it to refer to a different string. The map doesn't change. Map still has a reference to that same string. So briefly, I had, in this example, I actually had two references to that string. One stored in the local variable test, the second stored in that map. Then, after I update the local variable, the map doesn't change. I've copied the reference into the map. Doing it with primitive types works, very much the same way. The right thing to do here is just update the map. Right? I mean, if you want to change the map, you need to update it that way. Even if this local variable holds a reference to an object, reassigning it won't reassign the reference in the map because those are two separate references. If I call, as we saw before, if I call like a setter on that reference, now I'm actually changing something in the object that it refers to, and so those changes are reflected in the map because I'm not changing the reference, I'm changing something about the object that it refers to. That's a good question. Good review of references and how they work. Updated in the background. I'm just trying to figure out what that means, right? I mean, maps are pretty explicit, right? I mean, when I create a map and I add a mapping, the only way that I can change so again, I can change properties of that object, but the only way I can change what the mapping refers to is by updating the mapping. That would be kind of weird if it didn't work that way, right? Because it would be like, I mean, here's the idea, right? If I want to change the reference that's in a map, I've got to call map.put. That's the only way that that's going to happen. Now, like we said, we can change things about the object by using another reference to it, right? If I have another reference to the object and I call one of its setters, then both the map and the local variable will see that change because they both have references to the same object. But if I change a reference, local reference variable, if the map updated itself, that would be, I think, alarming. You could probably do this in like C++ somehow using references and things like that, like using pointers basically. But even there, it would be a little bit weird. There's a what's the name of the principle? The principle of least surprise, right, is a principle, that design principle that people use in programming languages and computer systems. The idea is that the behavior of things should be predictable and straightforward, right? If I have two choices about how to accomplish something, pick the one that would surprise the user the least, because people don't typically like to be surprised. Yeah, great question. So the question is about the map size, and absolutely. So, and this is a great question. It goes back to yesterday when we talked about hashing, right? So our, if we think about the actual hash value that we're using, the hash values that we're using here are really only limited to between 0 and 7, right? Because I only have 8 slots in my array. Hash code will return an int, and that's got 32 bits, so that'll go from 2 billion to negative 2 billion. But I'm already reducing that by half by computing the absolute value, since I lose all the negative values, and then I'm also doing the remainder by 8, and so now I get something between 0 and 7. The reason why that's okay, so keep in mind, we pointed this out yesterday about hashes, but it's worth reiterating. Whether or not collisions are a problem depends on the application. In Git, when we're using or anytime I'm using a hash to fingerprint something, if there's a duplicate, it's a huge problem. And that's why we use really, really, really big hash values. In fact, the hash values that are used by systems that do fingerprinting are way bigger than even an int in Java. An int is 32 bits. The hash function used by Git produces 160-bit value. So that's actually 5 times larger, right? And all those extra bits are there to take the probability of collisions and just make it small and drive it to 0, essentially, right? We can't get it all the way to 0. It's like, yes, is there a possibility that there are 2 files in the world that actually happen to hash to the same 160-bit value? Absolutely, there is, but it's so small that we don't have to stay up at night worrying about it. With this application, the reason why we've chosen this approach that's a combination of an array and a linked list is because the list is there to handle collisions. If we weren't planning, there are other ways to handle collisions, actually. There's another way that picks a big array. All right, so the approach that we're using uses an array, and then we handle collisions by using a list. There's another approach that uses an array, and the way you handle collisions is essentially by choosing the next spot. So imagine here is my algorithm. I compute the bucket. If that bucket is full, I move on to the next bucket. If that bucket is full, I move on to the next bucket. And I keep doing that until I find an empty spot. That's another way to do it that avoids using a list. The problem is that once at that point my map could only store the same number of entries as the size of the table, right? So my map could only store 8 values. The map that we created can store, an unlimited number of values, or it's certainly not limited by the size of the table, because when I get a collision, I use the list to link things together. And so here we're actually expecting collisions to happen, right? I mean, we would be nuts not to, because the table is only a size 8. Even if I made this bigger, like 32 or 64, right? I mean, the birthday paradox says that even if values are evenly distributed across those buckets, I'm going to see collisions pretty quickly. And so I need to have a plan, right? Maps that use this type of an array typically have a plan. They need to have a plan for dealing with collisions. Sometimes the plan is using linkage, which is what we're doing. Sometimes the plan is to just walk forward until I find an empty slot. That's another approach. But you need to be able to do something about a collision because they're going to happen. Yeah. So really, really great question. Yeah, absolutely. How can we access the key given the value? I think there is is that part of the map interface? I don't think so. Let's look. Let's see. So I've got values. I have replace, remove, put all. I don't think that it stores this. Yeah, and this is so if I need. So the question was, how do is there a way to get the key for a particular value, right? A map will typically not provide that operation. There's a couple of ways that you could do it. You could go through all the values, find the one you want. You could basically go through all the mappings, right? You could. There's a way to get all the mappings out of the map as a list. I could go through all of them looking for the value I was looking for. Part of the reason why this isn't a map operation, though, is also because it's not well defined. I can have 6 keys pointing to the same value, right? So now what's the key for that value? Well, you got choices, right? So a map is not one-to-one, right? It's one to, well, I don't know. My math terms are failing me here, right? But it's not invertible, right? I can have the same key mapping down to multiple values. Now, if I wanted to find all the keys for a particular value, like I said, I could take all the mappings for the map, filter them to only include the ones with the value that I'm looking for, and that would be either an empty or a non-empty list of keys. Sometimes it would have one, sometimes it would have multiple. Usually, if you need to do this sort of invertible operation, you just maintain 2 maps, right? There are some cases where the mapping is actually invertible, right? Where I expect to only have 1 key to 1 value, right? Something like those examples I was talking about before, right? Where it's like I have a piece of unique information about somebody that I'm using to find a value. Typically, if I have the value, well, not always though, right? Because think about it, the value might be somebody's name, right? I might have something that looks up your name based on your net ID. I could certainly have multiple values in that map that have the same name. And so if you give me a name like John Smith, what's their net ID? I don't know. I've got 6 options here. JS1, JS2, JS3, JS4, JS5. It's probably more like John S or J Smith 1, J Smith 2, J Smith 3, right? There is going to be more than actually a sort of fun exercise here. Illinois has a directory. let me actually. What? It says I've been blocked for performing too many. Okay, that's interesting. Oh, maybe I need to log in. Let's try that. Just want to see how many John Smiths we have here. I actually don't know what the most common name at the University of Illinois is. That would be really interesting to find out. All right. Name, I'm going to look for. Yeah, so it looks like we have 5 John Smiths here, 2 faculty, and 3 students. Well, okay, sorry, one of them is a Michael Smith. So I've got 1 faculty, 1 faculty, let's see here. Most common name. James is, anyway, so certainly among students, looks like they have different middle names. One of them's actually a Connor. Anyway, if you ask me if you give me a value, it's not necessarily true that I'm going to be able to produce a unique key. Yeah. Oh, I have no idea if you can use the directory search or not, but go for it. I don't know if you'd be able to see. Can you see other students? That would be weird. Well, anyway, I didn't design that, but okay, I guess. Hopefully there's a way for you to kind of mark your information as private. Okay, well, anyway. Not everything about, well, I don't know. I'm sure there's a reason for that. When I was in college, this was, I don't know, a long time ago, late 90s, early aughts, about 20 years ago. We had the campus had an email system. It was early. I think webmail was just starting to arrive by the time I graduated, but when I arrived in 98, many students were still checking their email by actually logging in using Telnet at the time to the campus mail server and then running a terminal-based mail program called Pine, which you can probably, let's see here, since we're having story time here. See if I can find a picture of what the Pine email client UI looked like. Yeah, there it is. Check it out. Oh, that doesn't look very good. Why is it? It's weirdly pixelated. It looked a little better than that. I bet I can find a better image online. Usually, I think it was green. Pine email. Let's see here. There we go. Yeah, this looks more like what I was used to seeing. That's better. Yeah. So this is kind of like, this is what you would. This was the UI for Pine. Here's an example of what it looked like for the compose dialog. It was pretty cool. I mean, it was email. It worked. It worked kind of the same way. It just, you would access it this way. What was kind of amazing about it on some level was that everybody on campus figured out how to do this, right? Like literally everybody had to figure out how to log into one of these shared login machines, run this sort of like terminal-based program. And that wasn't just computer science students, that was like everybody at the entire university. So, people want their email badly enough, like they can even figure out how to use, a basic Unix command line environment. So anyway, the point being that for a number of years, I don't know why they didn't turn this off, but there's a command. So essentially you can imagine everybody's logging into the same machine. It's kind of how it worked, right? It's an oversimplification, but and the other thing was that the machines that you logged in from frequently had names that were identifiable. We'll talk a little bit about this later in the week when we talk about the internet. But when you access this machine, you would access it from another machine on the campus network. And some of the names that the administrators had gave to those machines were actually like at least suggestive of where they were located on campus. And there was also another command that you could run, which is appropriately named finger. It was a strangely, it always gave you the sense that you were doing something inappropriate, which is sort of true. But you could look up information about a user on the system, and it would tell you things like where they last logged in from and when. And it turns out that this is like not super good information to expose for college students, right? And people would use this to do a certain amount of cyber stalking, right? Which was, I have no idea why they allowed this to go on for as long as they did, because I know that campus administrators knew about it, but there were at least a few relationships I heard that ran into trouble because people discovered that their significant other had been logged on at a machine at some other part of campus at 3 a.m. on Sunday morning or whatever. So anyway, I think we've improved since then in terms of the amount of information that you can obtain about other students. But the fact that the directory is open is still a little strange, I think. So anyway, digression, obviously. Yeah, I don't. Let's see here. I mean, let's see if I'm gonna see if there. Oh, I can still run this. Let's see if there's still a way to run some of these commands. I don't think they're going to give you the same, type of information that they would have in the past. I'll show you this in a second. Oh, okay, good. It's not even installed. Yeah. Yeah, so there was, again, since we were doing story time now, there was the other, the Harvard campus buildings are, date back to the dorms that we lived in. Some of them dated back to the 30s and 40s. And so when they were created, they certainly weren't set up with internet infrastructure. And at some point, the campus decided to put, add Ethernet, so that was certainly available when I arrived. You had an Ethernet jack in your room. There was no well, I think there was some wireless on campus, but not a lot. There certainly wasn't wireless everywhere. That came a few years later. But there were Ethernet jacks in the rooms. And, a lot of us didn't have laptops at the time anyway. They were kind of like a little still pricey and kind of considered a secondary machine rather than a primary machine. So I had a desktop computer like many other students. And, you plug it on the wall and stuff like that. And it worked fine. The dorm that I moved into my second year, one of my friends, who's actually now sort of a partner at a pretty well-known VC firm in the Bay Area, had discovered that the way that the house had been set up with Ethernet, and again, they've changed all this, meant that when you transmitted information across the campus, that part of the campus network, that information was available to everybody. So you could attach a device that was called a packet sniffer to the network, and you could, essentially vacuum up all the traffic for kind of like one half of the dorm, right? The dorm had maybe 300 students, 400 students in it. And, this was before the widespread use of end-to-end encryption. Nowadays, even if you could do that, networks aren't set up that way anymore, but even if you could do that, I would suspect that 99.9% of the traffic that you would be capturing would be encrypted, and so it wouldn't be something that you would be able to interpret. But at the time, again, this was early aughts, right? A lot of websites were still being run over unencrypted connections, and so there was, and none of this was done with any particular malicious intent by the students that I knew that engaged in it. They were curious, right? They were hackers, and they were kind of poking around, and they were just interested in seeing what they would find out. But at some point, I'm not going to do this in a recorded session, but a student and I did was it last summer? I'm losing track. No, summer 2019. It partly is the result of a really frustrating experience that I went through, but we discovered a pretty I think somebody could probably take this and run with it if they wanted to. A pretty kind of serious vulnerability. Well, it's not a vulnerability, but it was a way that you could really. We essentially found a way that you could lock somebody out of their Illinois account for kind of probably a arbitrary amount of time, and we told the right people about it. I don't know if they've ever done anything about it, but partly the reason we found out about it is this happened to me accidentally. And then once we figured out what was causing it, the student who's actually in one of the computer security groups on campus, I told him, I was like, let's see if we can replicate this. And sure enough, you can. So, if you decided that, this particular person that you didn't want to be able to get on the campus network for a couple of days, maybe a week or so, you can work that out, which is annoying. So anyway, Random stuff. I don't even know how oh, we got here because Ben brought up the directory stuff. Okay. All right. Any other questions about maps before we break for the day? These stories will be more appropriate for the next couple of lessons. So yeah, next few lessons we're going to keep giving you a chance to practice with maps, do a few more problems with them. We'll actually go back. There's actually a couple of places in the past where we should have used a map and didn't, because you guys hadn't seen it yet. And so we'll go back and pull a few of those problems forward and kind of take another shot at them and encourage you to use the map. In some cases, we'll have you return a map to kind of require that you use it, to kind of show you some examples of places where they're pretty useful. But any other questions about sort of the basics of this before we go? I'm not sure what this link is to. Oh, okay. Well, this is a picture of the. Can I move this? Let's see here. Oh, neat. Okay, yeah, that's strange. Can you turn this, or? Let's see. That's why I do this. Oh yeah, look at that. Wow. Seems, what is this for? Anyway, who knows? Somebody set something up and put it online, and then people start to play with it, I guess. All right, any last minute questions? Otherwise, tomorrow, what we're going to do is we're going to shift gears for the last two lessons of the week, and we're going to talk about some of sort of internet basics. So we'll do internet basics tomorrow, and then on Friday we'll talk about the basics of the HTTP protocol, which is something that you guys will be using on the next part of the MP, or at least at a very high level. So this is cool stuff. I think it sort of really explains, it's one of those topics that really explains a lot about the world and gives you a sense of actually what's happening with a lot of the devices that you use on a regular basis, and a lot of the tools and websites and things like that you use on a regular basis. So I hope you guys will enjoy it. I will see you then. Good luck on today's homework problem.